Now, the next type of flow meter uses what's called the Coriolis effect. It's Coriolis effect. It was named after a Frenchman who discovered the Coriolis effect, I think, sometime in the 18th century. This diagram sort of shows you how it works. Has anybody ever heard of the Coriolis effect in respect to anything else? Never heard of it? No one's ever heard of the Coriolis effect? Well, I'll just take a little bit of an aside then to tell you about the Coriolis. Has anybody ever, well, when you flush the toilet, are you aware of the fact that in Australia it goes round clockwise? Or when you let the water out of the bath, it goes round clockwise in Australia. Yeah? And in the northern hemisphere, it goes round anti-clockwise. There was a Simpsons episode all about it, where Bart had, was phoning up Australia, and that was when Bart came to Australia. Did anybody see that one? Yeah. That's the Coriolis effect that causes that. In the northern hemisphere it goes one way, in the southern hemisphere it goes the other way. It's not just stuff going down the toilet. In the northern hemisphere you have hurricanes. Hurricanes are strong winds that go round that way. In the southern hemisphere we have cyclones. Cyclones are strong winds that go round that way. It's all down to a thing called the Coriolis effect. And the Coriolis effect basically is that if something has mass, if something is massive, it has a mass, it weighs something, then once you start it moving in one direction, it wants to continue moving in that direction. And that's the Coriolis effect. The way we use this in pipes is we make a piece of pipe that has a little bit of a bend in it. And then, as this diagram here is showing, we flop that bit of pipe backwards and forwards. Yes, thank you, John. So we get a piece of pipe in a U shape and we flop it backwards and forwards. Now, if there's nothing in that pipe, or if there's something in that pipe, if there's no flow in that pipe, all that happens is it flops backwards and forwards. If, on the other hand, there is flow in that pipe, then what happens is the pipe, this is looking at it from the end, the pipe twists. So the pipe ends up twisting. I'll try and draw that. Kind of twists out of shape. And we measure, if we measure the twisting angle of that pipe, then we know how much flow there is in that pipe. The reason why the pipe twists is because the stuff in the pipe has got mass. And if the stuff is entering at this end of the pipe, let me get a better pointer. If the stuff is entering at this end of the pipe when the pipe is on its downstroke, then the stuff wants to carry on going down. Meanwhile, the pipe turns round and goes back onto its upstroke. Now the stuff has now got to here. The pipe's on its upstroke. No, the pipe is... Yeah. No, I got that completely wrong. Let's start that again. I have a bit of fluid. The fluid enters the pipe at this end. The pipe is on an upstroke at the time, so the stuff's happily on an upstroke. A little bit later on, the pipe turns round. The stuff has moved from one bit of pipe to another bit of pipe. So the stuff which wants to go upwards is now being forced to go downwards by the pipe. So the stuff says, no, I'm not going to go downwards, I'm going to carry on going upwards. So what it does is it pulls the pipe out of shape. And that is the twisting that we see. If we measure that twisting, we know how much mass has just gone past. The important thing about the Coriolis flow meter is it measures mass. It measures kilograms per second. The Coriolis flow meter measures mass. The thing about the Coriolis flow meter is it doesn't give a rat's about what the flow is doing. It doesn't care if the flow is swirling, if the flow is going up and down. It doesn't care. All that the Coriolis flow meter will give you is the mass. It gives you the mass in kilograms. As an added bonus, by measuring the frequency at which the pipe is able to flop up and down, the Coriolis flow meter also gives you density. So the Coriolis flow meter will give you two things, mass and density. It is completely immune to flow, to velocity. It's completely immune to air bubbles. It's completely immune to solids. All it gives you is density and mass. The Coriolis flow meter is to all intents and purposes absolutely accurate. It is completely and utterly accurate. There's only one lab that I know of in the entire world where they calibrate Coriolis flow meters, and that's in Switzerland. So there's only one place in the world where these things can be calibrated. They are absolutely and utterly accurate. They will measure all flows. Now, let's have a quick think about this. Coriolis flow meter. Just have a look at some pictures of some. Here's the principle then. We have a bit of bent pipe, we wobble it backwards and forwards, and we measure the bend in that, the twisting in the pipe. This is what they look like, some small ones. Now, a couple of things about the Coriolis flow meter. Firstly, it's completely and utterly accurate. Secondly, it's not cheap. This one here, it's about, to give you an idea, it's about 1 meter long, and the pipe is about 100 millimeters. This one, I've recently been told, is being sold for $26,000 for that one. And that's if you get on well with the salesman and he gives you a discount. They're not cheap. This one over here, the smaller one, you could probably pick one of those up for around about $10,000 to $20,000. This smaller one, we're talking about a pipe diameter of about 15 millimeters, 20 millimeter pipe diameter. So the Coriolis flow meter is not a cheap option. On the other hand, it's absolutely accurate. It gives you mass in kilograms. Let's have a look at a couple. These are some small Coriolis flow meters. Before we go on too further, Coriolis flow meter, will it measure gases? In actual fact, gas, when we're measuring gases, we just want to measure, you know, it's just liquid, it's just a mass going past. Gas has mass as well. So the Coriolis flow meter will absolutely measure gas accurately, because it measures everything accurately. And in many cases, the Coriolis flow meter is the only way to accurately measure gases. Will it measure water? Yep, it will measure water quite happily. Will it measure oil? Will it measure water with air in it? I'm assuming the ticks are still up there, because yes, it will. Will it measure water with sewage in it? Yes, it will. Coriolis flow meter measures everything. Another thing the Coriolis flow meter will measure is gases with small particles in them. You see, when you make tablets, if you were to make a small blue diamond-shaped tablet like that, pharmaceuticals I'm talking about, then the way you make this is you get a pipe and you blow air through that pipe, and in that pipe you also blow powder, and you blow tiny amounts of powder into tiny little diamond-shaped molds, and then you squash that mold and you make a little tablet. And those tablets sell at something around about $500 a head. Unfortunate name, really. About $500 a tablet. So pharmaceuticals is massive money-making industry. They're selling tiny little tablets for $500 each. Pharmaceuticals is one of the industries that use Coriolis flow meters, because all they need to do is they need to put 1/4 of a gram of this and 1/8 of a gram of that and 1/10 of a gram of the other into this tiny little mold. And so they use Coriolis flow meters because they are absolutely accurate. And they will measure the powder in an air pipe absolutely accurately. So they're one of the users of small Coriolis flow meters. Another industry, see, these things are so expensive, only industries that are rolling in money can use them. Another industry which is rolling in money uses bigger Coriolis flow meters. Now look at that monster. You're not going to get a lot of change out of $10, $15 million for that. And the other industry which is rolling in money but depends on accuracy is the oil and gas industry. If you're filling an oil tanker up, a 2% error in filling an oil tanker up is just not acceptable. So a Coriolis flow meter would be used to measure the flow into an oil tanker. The other thing about the Coriolis flow meter is if it's being used to measure gas, if we buy gas by kilograms instead of buying it by litres, then it doesn't matter what temperature it's at, because gas, when it's hotter, takes up more volume. So by selling gas by the kilogram rather than by the litre, we have a system which is independent of the temperature of the gas. And that's very important, especially when you're filling up a tanker full of gas. So the companies that use the sort of industries that use Coriolis are the sort of industries that can afford to use Coriolis: pharmaceuticals and oil and gas. Now, looking at these big Coriolis meters here, bear in mind the way it works is by plopping that big pipe backwards and forwards repeatedly and measuring how much that big pipe twists. Can anybody see the Achilles heel of the Coriolis meter? Metal fatigue. Yes, absolutely. A Coriolis meter has got a limited lifespan. Not exactly sure how long that limited lifespan is. It's going to depend on what you're putting through it. If you're putting mineral sands through it, you might only get a year out of it. And a year out of a meter that just cost you $26,000, that doesn't sound too good to me. But some industries will quite happily live with that. If your mineral sand happens to be gold, well, yeah, that's reasonable. But if you're measuring something a little bit less profit-making, then maybe it's not reasonable. So the big thing about the Coriolis flow meter is that we're physically bending the pipes, Sooner or later, that pipe will suffer from metal fatigue. Sooner or later, that pipe will crack. It has a limited lifespan. And you can't just replace the pipe. You have to replace the entire meter. So that's the Coriolis flow meter. It's like the king. It's the Rolls Royce of flow meters. The next type of flow meter we're going to look at is the vortex flow meter. This works on the principle of a flag in the wind. So, I'm just going to draw a flagpole. Here's a flagpole. When the wind blows, here's the wind blowing. When the wind blows, the flag flaps. The faster the wind blows, the more the flag flaps. The reason for this is because of little vortices that build up on the sides of the flagpole. Now these vortices build up and break off from the sides of the flagpole, and they travel away from the flagpole. They alternate, one side and the other side, one side and the other side, and they break off and they travel down, and then the flag wraps itself round the vortices. That's the principle of the vortex flow meter. Couple of improvements. A round pole doesn't make nice vortices. To make nice vortices, you need to have a sharp-edged pole. So we use a sharp-edged pole that we call a bluff body. That's the first refinement. The second refinement is we tend to make the flag very, very solid. Pretty well a solid chunk of steel. And then it flaps by a few nanometers each way. So very little flapping, just a couple of nanometers each way, and the bluff body is creating nice, strong vortices. One from one side, the other from the other side. So that this is what a vortex flow meter looks like. You have a bluff body here, creating the vortices, and you have a flag here, which flaps backwards and forwards. It's just like a flag in the wind. And just like a flag in the wind, the faster the wind blows, the faster it flaps. Now the one problem, this is what vortex flow meters look like, they tend to be very, very solid. We use these for measuring things that we can't easily measure other ways. Basically nasties, and real nasties. Things like steam. Steam, superheated steam or saturated steam, is very, very nasty. It's very unpleasant and it tends to damage flow meters. The vortex flow meter will happily measure saturated steam. And here's a little diagram showing the principle. So we have the bluff body, the vortices breaking off each side and travelling down the pipe. And then the flag, and there's not much to the flag is this bit, flaps up and down by a couple of nanometers. The one problem with the vortex flow meter is, same as what, well, I'll ask the question, what happens to a flag on a flagpole when the wind isn't blowing very much? It flops down. There's a cut-off point. Basically, you need to get to a certain velocity before it starts to flap. It's the same with a vortex flow meter. There's a very, very sharp cut-off point, and below that velocity, it doesn't measure anything. So it's a good, accurate flow meter, but if the velocity is too low, it measures nothing. and then it suddenly starts reading when you get to the correct velocity for the flag to start flapping. So these are used quite commonly in nasty things that we can't easily measure other ways. Now, will it work with gases? Yes, it will. It's designed to work for gases. Will it work with water? Yes, it will. It will work with water. And oil? Yes, it will work with oil. Providing we're maintaining the velocity through the thing, it will work with those. Liquids with gases inside them? Yep, it'll work just fine. How's it going to do with sewage? Yeah, big fat bluff body. That's not going to do very well with sewage, is it? It's not going to do very well with toilet paper. So, not such a good use for that. Also, sewage doesn't tend to be flowing fast. So it doesn't do well with slow flows. The next method of measuring flow is the ultrasonic flow meter. There's two types of ultrasonic. What's called time of flight, which is also sometimes called transit time. So, I'll look at this. Time of flight, or transit time. And the way the time of flight one works is you have a transmitter and you have a receiver. So come here, transmitter and receiver. What happens is the transmitter sends out a pulse of sound. Now you have to have some sort of carrier inside the flow. You have to have something inside the flow, such as an air bubble or a particle of dirt or something, some sort of impurity in the flow to be a carrier. So it sends out a signal to the carrier. The carrier moves down the pipe, and then when it gets near to the receiver, it sends that sound pulse to the receiver. All we need to do is measure the time it took to go from the transmitter to the receiver, and we know the speed at which the carrier was moving. If we know the speed at which the carrier is moving, we know the speed at which the fluid is moving, and so we know the flow. Time of flight, transit time. The nicest thing about the ultrasonic flow meter is that we can retrofit it to the outside of the pipe. The very nicest thing about the ultrasonic flow meter is that you can put it on the outside of the pipe, which means if we have extremely nasty things on the inside of that pipe, it doesn't matter, because the flow meter is on the outside. Providing the sound pulses can get from the transmitter and the receiver into the fluid, it's going to work. The sort of things that can stop it could be if you have insulation on the outside of the pipe. Well, that's going to stop the sound. If you have a very spongy pipe material, and a spongy pipe material, sort of things like old cast iron. Old cast iron was quite spongy. That will probably stop the sound. But if you have or very, very thick plastic pipe. Thick plastic pipe will stop the sound. On the other hand, thin stainless steel metal pipe, it will go right through it beautifully. Thin plastic pipes, it will go right through beautifully. It will work lovely. It's on the outside of the pipe. It doesn't matter how nasty the stuff is on the inside of the pipe, the flow meter still reads. It's not specially accurate. with the best will in the world, you're going to be lucky if you're doing better than 2% accuracy with it. But it's on the outside of the pipe. They come in kits. This is, the bottom one here is showing a kit form that you can strap onto the outside of the pipe. What I've done in the past is I had one of these kit form flow meters and I used it as my spare for all the flow meters in my factory. Because if anything went wrong, I could take this thing along, strap it onto the pipe, and then I'd take the 4 to 20 milliamp signal, strap it onto my ultrasonic, and I could be reading flow again within 15 minutes. And that then gave me a chance to do the really serious fault finding on whatever's gone wrong. I lose accuracy, but generally speaking, the production people don't even notice. It's just it'd be great. I recommend you have one of these little strap-on ultrasonic flow meters in your toolkit. They cost $2,000 or $3,000, but it'll pay for itself in the first call out. So that's the time of flight one. You do need to have something in the fluid to be a carrier. So let's have a little think about this. Will it work with gases? Maybe, probably not. May work, may not. Hard to say. What about water? Normal, say, drinking water. Yeah, it'll work for stream water, drinking water. I'll be happy with that. Because there's lots of air bubbles. There's lots of little things in there. Oil? Probably work with oil if there's bubbles in there. Probably. Liquid with gases in? Yes, it'll work for those. And liquids with solids in? Yes, it'll work with those. There's one proviso. If here's your pipe, if you have air bubbles in the top and slurry in the bottom, you have to make sure that you don't put your ultrasonic sensor at the top or the bottom, because the air bubbles and the slurry will kill the sound. So you have to make sure, if you do have air bubbles or you do have slurry, that you mount the sensor on the side so that it's not going to be affected by those air bubbles. Anything inside there that can absorb sound will stop it working. Like I say, it's not especially accurate. Now, before we move on, there is another type of ultrasonic flow meter. And the other type of ultrasonic flow meter uses, I'm going to probably spell it wrong now. How do you spell it? 2 P's. Doppler. The Doppler effect. Now, the Doppler effect is what the cops use on their little radar gun. The Doppler effect says that if you send out, I'm going to do a little radar gun. If you send out pulses, either sound or radar, and it bounces back off of something, then those pulses bounce back. If the object is moving towards you, then the frequency goes up. If the object, on the other hand, is moving away from you, the frequency goes down. Now, the other thing is, the faster the object is moving, the more the frequency goes up. Now, you've probably experienced this before in your lives. If you think about a race car, when a race car is moving towards you, as it moves towards you, it has a high-pitched sound. When it moves away from you, it has a low-pitched sound. So that as a race car goes past you, it goes meow. high pitch coming towards, low pitch going away. And the faster it's moving, the more there's a pitch change. So a very fast-moving race car would go meow with a big pitch change. So have you all heard this before with cars or objects moving past you? Okay, so the faster it moves, the more the frequency changes. So if you had a very fast-moving car, say, for instance, a French one like a Citroën or a Renault, it would come past meow. Whereas if you had something like a Ford or a Holden, it would come past meow. So that's how you can tell how fast things are moving, by the frequency change. This is used to measure velocity, and we can use it to measure velocity in pipes. If we've got a bit of pipe, you can get a little Doppler sensor that sends out sound waves into the pipe, and if there's any sort of particles in that pipe, the sound waves bounce back, and they'll bounce back with a different frequency. And that frequency shift tells us the velocity they're moving. One of the places they use this type of flow meter is, of course, on the ultrasound machines. If you've ever been into hospital with a pregnant wife or to have your heart checked out, then they'll stick a ultrasound Doppler machine on you, and that ultrasound will not only tell you the baby's healthy, the sex of the baby, all of that sort of stuff. They'll also measure things like the velocity of the blood going through the blood vessels. And they can measure to see how healthy the baby's heart is by the speed at which the blood flows through the blood vessels. So that uses the Doppler effect. The Doppler effect is not very accurate. Irrespective of what the cops tell you, Doppler radars are really not very accurate. You'll be lucky if you get much better than 5% accuracy out of one.